Aloha, welcome back. Thanks for sticking around for the last session of the Science Summit. This session will be focused on sea level rise adaptation. And yep, everyone's coming in. So aloha, and I'm going to get started. My name is Heather Kirkering, and I am with USGS, the federal side of PI-CASC, the acting deputy and science coordinator. Great to see all of you here, many familiar faces, and I'm excited for this next session. So just to give you a quick, really quick rundown of the importance of sea level rise to PI-CASC and some of the investments we've made. You'll hear about them from some of the principal investigators or researchers that we've funded, and then also managers that we've worked with throughout this session. So one thing I wanted to point out, although this session or this summit is focused mainly on the state of Hawaii, PI-CASC doesn't include the state of Hawaii as well as all the US affiliated Pacific Islands. And so the snapshot here displays that region, but I also wanted to note that the sea level rise work that we funded includes that entire span of space through Hawaii, RMI, the Marshall Islands, Micronesia, projects that are region-wide, so encompass many of the different islands and territories, and American Samoa. And since 2019, we've actually invested over $3.5 million on projects that are specifically focused on just impacts to shorelines, but also encompasses a lot more that sea level rise can impact. And so I wanted to show you this total soup of logos, which I know you've seen throughout the summit this week, of just all the different players and organizations that it takes to make anything happen or to start identifying priorities, addressing them, and creating applicable science that can be used by end users, and also further our ability to adapt and build resiliency. And so, you know, as I was just saying, we do support like the science and the technical side of bringing models to the table, bringing data to the table, and really understanding what's happening on that level, but also working with what does this actually mean for the people who are managing resources, not just biological or ecological, but also infrastructure and other elements that are being impacted by sea level rise. And so these projects, and hopefully you'll hear about them and just a little bit in terms of how they are really representative of the partnerships that we try to promote and the co-production of science that we try to promote, so that it can be a useful tool or useful information that we provide. So thank you to all of these organizations and people affiliated with them that have helped move some of these projects forward. And then, you know, still on that note, these are components of sea level rise focused projects that we've supported that really address other elements that you might not think of right away. How does sea level rise or sea level change or anything impact food security, our freshwater security, which is key on the islands, which you've heard about a lot in the summit so far, impacts to our cultural sites and heritage, ecosystem services. You can read on, but public access, watershed health, what resources are out there that can help our islands be more resilient to sea level rise, such as coral reefs or mangroves, and on the reverse, how does sea level impact those? So, and then again, economies. We all know how important our beaches are to the economies here. So my role right now was to give a really brief intro to our investment in sea level rise, but to also share this introduction with Brad Romine, who is the University PI-CASC Deputy Director, to talk a little bit more about what PI-CASC is doing with that. Thank you.
Okay, aloha everybody. Thank you, Heather, and thanks everybody for sticking with us for the afternoon. I would like to share one example of how we're working to improve communication and cooperation in sea level rise adaptation science in Hawaii and the Pacific Islands through initial series of dialogues convened by PI-CASC in cooperation with Hawaii Sea Grant. Resource managers, planners, and communities are readily using the scientific information that's being produced in decision-making and planning for sea level rise. Some of our science partners approached us over the past few years, concerned that better cooperation is needed, though, among these researchers and science users, our communities, to improve awareness, consistency, collaboration, and clarity about appropriate use of these research products, and to meet ongoing and emerging science information needs while maximizing that shared capacity and avoiding duplication of our efforts. In response, we convened a series of 3 initial dialogues to discuss improving communication and cooperation among research groups and science organizations working on sea level rise adaptation science and management applications in the Pacific Islands. The first discussion was a focus group of researchers and science organizations where we shared recent and ongoing research efforts related to sea level rise impacts. In the second discussion, we expanded the group to include managers, resource managers and officials that are applying this science in our communities and with our communities in their planning and adaptation efforts to better understand their uses of the information and their evolving and growing needs for this scientific information. In the third meeting, we reconvened the initial research and science organization group to dig deeper into discussions and takeaways from the first 2 meetings and discuss next steps. And I just want to extend a big mahalo to all our participants in those initial meetings, including some of those here today. And we look to expand those discussions to more folks, and this effort is part of that. So some of the next steps identified by the focus groups was to establish and expand a Pacific Islands Sea Level Rise Science and Action Network, or something along the lines of that name, with some management capacity to help us organize that. We also want to try to increase 2-way communications to share and discuss network partner efforts, convene sea level rise science action dialogues and symposia. Again, this is part of that effort. And develop an online information platform to share research and management applications. And that last bullet is what I want to share with you here next, really briefly, is to address that last bullet. We developed this online information platform to share research and management applications, which we're calling the Pacific Islands Sea Level Rise Project Explorer. The story map and interactive mapping tool provides a brief overview of recent sea level rise science, a description of the sea level rise dialogues that we've held so far, and I think most interestingly and unique, an interactive map series to explore projects shared by our science partners so far on sea level rise adaptation science in the Pacific Islands. The projects are also grouped in the maps under other 3 tabs, such as management applications, the different sea level rise impacts that they're mapping and modeling, and the science information tools related to those research efforts. I want to extend a big mahalo to the researchers who so far have shared their projects. We're looking for many more to add to this. So if you have ideas of projects that we should get on there, please do explore the tool. There's a QR code there. Don't know if we got the website address up there, but next one on the bottom. Okay, thank you. There it is. Pacific Sea Level Rise Projects.org. And I want to give a big mahalo to Patrick Grady, our GIS guru at PI-CASC, for helping us put this together, and Rachel Lenz for her help in building this tool. So just a real quick example, you can zoom into any of these areas of the Pacific Islands region. Click on one of those marks for one of these projects. Here we're showing an example of a project from Dean Gesh with the U.S. Geological Survey in the Marshall Islands. There's information on the project, location, project partners, and applicability for planning and management, and much more. And of course, links to more project information. So I hope you all take some time to explore that tool. And again, we hope to continue to build on the dialogues and this effort and this Project Explorer. Please approach us at this meeting by email, by phone, if you have ideas for expanding on this and for continuing conversations. All right, thank you. I'm going to pass it back to Heather for our series of research presentations. Thank you.
Thanks, Brad. I'm personally very excited for our lineup of speakers to see them in person again, and then to also just see the efforts and the updates on the work that they've been doing. So the first speaker in our series is Tara Owens. Tara is extension faculty with the University of Hawaii Sea Grant College Program, specializing in coastal processes and coastal hazards. Partnered with the County of Maui Planning Department, her role is to bridge the gap between science and policy and planning for improved community resilience. She also interfaces with other government agencies and community on collaborative projects pertaining to coastal management, coastal erosion, and sea level rise impacts. Thank you, Tara. Please give a round of applause.
Well, aloha. It's been a long time since I've been up on a big stage behind a big podium in front of a big audience. Makes me nervous, but I'm also so excited to see everybody again. So thank you for having me, and thank you for the introduction. Just so you understand my role a little more, I live and work on the island of Maui, even though I'm extension faculty here at the UH Manoa-based Sea Grant program. And on Maui, I'm partnered very closely with the whole county, but specifically the planning department where the coastal zone management program operates. So we're tasked with, well, I guess in my role, I sort of get to have one foot in the world of university academic research, and then the other foot in the real world. And that's how some of these projects are born. And this is one of those. So just to get started, this is a focus on a couple of tools we launched for West Maui fairly recently. There's a whole team of folks involved in this effort, and I get to speak on their behalf today. So you see the logos along the side, common theme, PacIOOS, Sea Grant, SOEST, SIMAR, formerly known as JIMAR, and so on. And we have a couple of our team members in the audience today to help me out when I need to phone a friend. As quick background, the real imminent issues that are occurring on Maui have to do with high waves and coastal erosion, and that of course are magnified by sea level rise. And we have severe impacts island-wide. So you can see a montage of photos here from all around the island. The top left photo there is from West Maui, and on the bottom, West Maui, West Maui, West Maui. So that's a common theme. West Maui is a really important economic center, historic center, cultural center, and it is one of the hardest hit areas, I'd say statewide, when it comes to sea level rise and those impacts. So while that's all happening, I know this crowd is all aware that the Sea Level Rise viewer was launched back in 2017. And with that, it quickly became on Maui part of household conversations, and that information has been institutionalized in the planning process. So we've got vulnerability assessments going on island-wide for all sectors of the government, community plans, regional resilience projects, shoreline setback policies, hazard mitigation plan, water use plans, and now a new managed retreat revolving fund. All these things are relying on that information. And it's really wonderful to have nationwide or statewide information like this that we can use consistently. But I like to emphasize there's always still the need to have more locally or regionally specific information that can support a community's effort. And that is where we have been focused on West Maui with these tools. And so this team set out to develop two distinct tools. The first being what we call the wave run-up forecast, which is a site-specific wave run-up forecast for the coming 6 days to signal potential impacts and inform preparedness. The second tool is the West Maui wave flooding tool, which gives us site-specific future scenarios with sea level rise to inform longer-term land use planning. And West Maui is a really interesting place. So before I demonstrate the tools, just mention a few things about why West Maui is a special case. So two takeaway messages. The first is that there's a lot of variability in the way that waves affect the West Maui shoreline. So the team set out to develop this next generation wave model, and it's tailored to West Maui, and it's really good at capturing this variability along the shoreline. And so by variability, I mean that some areas are going to have more flooding or impacts than others, even under the same sea level rise or the same wave scenario. So the reason for this variability is if you look on the left-hand side, the image there, that's the bathymetry in the Maui Nui complex. So between Maui Island, Molokai Island, and Lanai Island, you can see the purple colors there, the really deep channel between the islands, and the lighter blues and oranges and yellows and greens are the shallower areas. But what that essentially means is that this causes the waves that are coming into that complex to bend and form these fingers of wave energy that you see over on the right-hand side. These are some modeling examples from looking at a south swell and a north swell and that wave energy coming in. So you can see the fingers coming into the West Maui coastline, just showing you how variable the wave energy can be and therefore the impacts on the shoreline. The second takeaway is that sea level rise will continue to increase the wave energy at the shoreline. So if you're looking at this slide here to demonstrate that under quote unquote today's normal conditions, you get some protection from wave energy from the islands of Molokai and Lanai as they come into the coastline. But if you get like a big seasonal swell, you get some of that wave energy crossing over the reef and reaching the shoreline. Of course, as sea level rises in the future, looking ahead, that same swell is going to come into the coastline and substantially increase the flooding that happens at the coastline and the impacts of it. And we're already seeing that. So that is the basis for the two tools that we've now put together and recently released publicly. So the first tool is the 6-day wave run-up forecast. So think of this as like a weather forecast for waves. You're looking at, is it going to rain this week? It's going to be dry this week, it's going to be hot. What are our waves going to look like? So again, this locally specific wave model, you can see those fingers of energy on the left side, was then calibrated. This was the fun part of the project, with on the ground photos of wave impacts that came or were collected by the community through a web app. And the previous speaker on the panel from the USGS had me thinking about this. Of course, we had this cadre of people from the community who did this because they love Maui and they love their community and they don't want to see bad things happening. But while I get paid to do my job, they didn't get paid to collect this information for us. And that is a model we should change. So that was a good reminder. But it was an important part of the project, and their photos then gave us information about what does it mean when this type of wave comes into the coastline, and when does that trigger an impact? And so then you look at the forecast over on the right-hand side. You can see those blue lines in the forecast. This is for the Kaanapali section of the shoreline. If those blue lines reach up into the red area, that means there's going to be likely impacts. And so zooming in onto another example, this is from Kahana area in West Maui. This is from the last few days. You can see within the last few days, the blue did reach into the red area. There probably were impacts occurring. And if you can see over to the right-hand side, there's a letter A and a letter B. Those indicate some impact thresholds that we set for these different areas. A being light impacts, B being hazardous impacts, and C, if we get to that point, are critical impacts. And if you click on the run-up examples tab along the top, you can even see photos that came from the community of what these types of light, hazardous, or critical impacts might look like, some real world examples. And the thinking with this tool as we continue to engage the community and make sure everybody know it exists is that, okay, how would you use this? It's a preparedness tool. Maybe you change your commute patterns. If you know there's a big wave day and you've got to drive to West Maui, maybe you want to time your commute not at high tide when the waves are going to be flowing over the highway. Maybe if you're a property owner, you deploy sandbags to protect your property from flooding. Maybe you remove lawn equipment. Maybe you are just aware and not caught off guard, which is also really important. And then the second tool is the wave flooding tool. So we just saw that changing water levels will change how the waves interact with the shoreline. And we know there's going to be increasing wave energy with climate change. So this tool helps us to look further into the future to reveal potential vulnerabilities for planning and engineering. So what this tool does is it visualizes flooding over the land from a combination of sea level rise, tides, and then adding waves on top of that. And so this moves us toward this concept of total water flooding, so all the sources of marine flooding, excluding inland flooding. And so we've tried to simulate these long-term flooding scenarios with sea level rise, and we have various wave heights. You can choose, if you look over in the navigation box over on the right-hand side, you can choose wave scenarios from minimum wave height, annual high wave height, or a maximum wave height, sort of this total water level again. And then click from various sea level rise scenarios, 0, 1, 2, 3, and 6 feet, as it is now. And you can visualize the flooding over the land from those combinations and scenarios. And we even have a choice for wave direction, which is really important in West Maui. Because of the shielding from the other islands, we know that we get greater impacts when the waves reach a direction that is very, very north. And so that can be very important for West Maui. And one other interesting thing about this tool is that you can click in any of the flood areas and you can get flood depth. And that can be something that can be useful for planning and engineering. So as it stands right now, the planners I work with on Maui, they, when they're looking at maybe a development application, they might go first to the sea level rise viewer. And then for West Maui, this is an additional tool or a layer on top of that they consult to maybe think about siting of new development or mitigation or adaptation for that development. So in closing, I guess before we transition to questions or discussion to the next person, I should tell you where to find the tools. You can go to the PacIOOS website, www.pacios.org. And if you click on the top for shoreline impacts, you will be able to find a link to both of these tools. And lastly, I wanted to mention that while we didn't necessarily set out to do this, because we were focused on West Maui, we are pleased to be able to report that this model is being looked at to be applied statewide over the next several years. And I don't know if Chip will be talking about that in the coming talk. I hope so. So that's another great outcome. And thank you very much.
Hello, Tara. Yes, we have time for one question. Go ahead, Jessica.
Your team's done awesome work. These are great tools. And I'm hoping to hear a positive answer to this question. Is the National Weather Service integrating your tools into their daily or weekly or major event forecasts? So that I know that in some parts of Alaska, our weather service does. And so when we get statewide alert, not statewide alerts, but local alerts on our phone, it's based on like sciencey stuff like your tool. So I see NOAA up there and they're National Weather Service people too. So I'm wondering if it's integrated yet.
You hoped for a positive answer. I don't know if this is going to be that positive answer. I would say, and I can have my friends in the audience respond if they feel the answer is different. Not yet. Of course, this tool was built specifically for West Maui. It's relatively new, and we're still watching as these waves come in and making sure the model is calibrated the way we want it to be. But I think one of our ambitions all along was to work with the Maui Emergency Management Agency, which does send out community alerts via cell phone when there's potential coastal flooding or high wave impacts. And so there may be a way, and they've been open to that, of including alerts in their system specific to West Maui when we do, I think we have a triggered impact.
Thank you.
Hello.
Thank you. I'm sure there are more questions. We're going to keep moving through the speakers. So next we have Dr. Phil Thompson. He's the associate professor at the Department of Oceanography here at Manoa and the director of the University of Hawaii Sea Level Center. He serves as the principal investigator for research projects funded by USGS, NOAA, and NASA, focused on understanding decadal climate variability, future tidal flooding, and the interaction of sea level and waves in the nearshore environment, excuse me. An emerging theme in his work is co-production of research that facilitates science-based coastal management and digital tools that support effective science communication. This is next. Thank you. Great to see you.
Thanks, Heather, and good afternoon, everyone. Aloha. Yeah, so I'm going to talk about two things today, both of which were funded by PI-CASC. One of the great things about working with PI-CASC is that not only do you get funding support, but they also connect you with the stewards, the stakeholders, the decision makers that you need to interact with. And you'll see a couple of examples of those folks here in this work. So the first project I want to talk about is at Puhonua Ohonaunau National Historical Park. So this is a really important culturally, from a cultural perspective, and also a historical perspective in Hawaii. And unfortunately, the park assets are vulnerable to sea level rise, and the impacts are increasing in frequency and severity. And so here's a picture of Marianne McGray. She's the supervisory archaeologist here at the park. And so we've been working with her to develop some questions that we can work on to help her make decisions in the future about sea level rise and how it will affect the park. We're going to look at the extent and frequency of flooding and how that changes over time, how the character of that flooding changes, and also how we can effectively communicate to the people that hold the purse strings or just visitors to the park. So the first thing we did, and actually this is another connection that the PI-CASC made for us, is that we worked with Jeff Danielson and Dean Gesh at USGS CONED, and they came out to Hawaii, to this park, and flew LiDAR, did some ground-based LiDAR and GPS surveying, and they did some flew drones, and created this incredible DEM that you can see on the screen here. Hopefully you can see it okay, but it has incredible horizontal resolution, 1 meter resolution in the horizontal, and very high accuracy in the vertical. And this really enabled us to be confident in the models that we're running, that we're getting the spatial variability around the park, kind of like what you heard from the last talk. You can notice a couple of things here. I think you can see it. So right near that black square, that black circle in the picture there, there's like a backwards L shape, kind of in red. That's the boundary of the Pu'uonua. It's the Great Wall, and inside you can see like a little red rectangle. There's a heiau in there, and then inside that black circle, that's sort of some low-lying area that the park visitors frequent quite a bit. And then all of this, if you look at the color scale there, is less than a meter above mean high water, or the average highest tide of the day. So there's not a whole lot of breathing room here in terms of what can happen here with the park in terms of sea level rise. So what we did was we looked at, we first set up a wave model, different model, but similar to what was done in the last talk. We put out some water level sensors around the reef, those little magenta circles that you can see up there, if you can see them. Those are places where we put water level sensors, so we could have some observations to then tune and validate our model to make sure it's realistic. And then this is just a snapshot of the water level from the model. And so you can kind of see the waves kind of coming in and wrapping around and wrapping into the park. So some quick results here. So what we did was we looked at different types of events. So we looked at where the extent of the impact for current average high tide, for a high sea level event, like a king tide event, something that might happen like 2 to 15 times per year, depending on the conditions around Hawaii at the time and the year we're talking about, how high the tides are. And then we looked at a 1-year event. So something like that like the largest event you would get in 1 year on average. And then a 10-year event, or the largest event you would get during a decade on average. And so that's what's shown here in the figure. The black, the grayscale here, the darker colors are just higher elevation. This is all dry, the grayscale. Then the different colors here correspond to different extents under these various conditions. So the dark blue here, that's average highest tide of the day. The pinkish color, which you don't see much of, that's sort of the king tide flooding. And you see there's not a whole lot of impact from king tide flooding or just high tide flooding in the park at this particular time. This is for current. And then the 1 year and 10-year waves are in the orange and yellow. And you see how there's some impacts throughout the park for those larger extreme wave events. That's pretty consistent with what we hear from the park managers at this point in time. So really the impacts are confined to very large wave events. And that's the take home here. What we want to know is how this is going to evolve into the future. So for that, we reran the model under different scenarios in the future. I'm going to show you just like one scenario in a sort of a near-term time period using the intermediate scenario from the recent interagency task force report that provided those sea level rise scenarios that are very popular and used often in planning. So this corresponds to 16 centimeters of sea level rise by 2045. Now, in addition to that, I also want to point out that the tides vary from one decade to the next as well. And this is actually another project that was funded by PI-CASC that I looked at, the variation in tides in Honolulu. And so the tides vary from one decade to the next. So from 2035 to 2045, for example, the average height of the high tides, just purely from astronomical forces, will go up by about 7 centimeters. So you have to add that on top of the sea level rise itself due to climate-driven processes. So when we consider the changes in the future, let's first look at 2035. So there's two similar maps to what I showed you before. On the left side here is for 2035. And so what you see here is it actually looks pretty similar to the current situation. There's not a whole lot of change in the near term over the next 10 to 15 years or so. You see very little of that pink color corresponding to high tide flooding. There's a little bit of an expansion for those higher wave events. But by and large, it looks somewhat similar. And a lot of that is because there's some topographic constraint here. So if your eye followed around the edge of those yellow and orange colors, then there's an increase in elevation pretty sharply right around that point. And so there's only so far that the inundation can go, the flooding can go. But what that means is that even though the extent isn't changing, but the character will change quite a bit. So now the right side over here is 2045. And what you see now is that inside the Pu'uonua and also in that sort of low-lying visitor area where people frequent, there's a lot of that pink color. So we've gone from being dominated only under the largest swell events do you get impacts to now having routine flooding multiple times per year, potentially up to 15 times per year of just high tide flooding in the park. So that's a big shift in the regime and how you deal with the impacts from sea level. And this is not that long away, right? This is a couple of decades. So there's a lot of work to be done to figure out how to deal with this. Oh, yeah, and this is fun. So this is to present these results and kind of like a whiz bang, sort of really motivating people to think about and to take this seriously. We created an augmented reality app to view these results. So this is me in my hotel room a couple of weeks ago at a conference, just on my hotel room desk, projected a model of the park onto my table. And then you can zoom in and kind of walk around and you can change the amount of sea level rise. You can look at different scenarios and explore the park that way. We don't have the wave information in here yet, but we're going to add that as well. So you'll be able to see those layers too. And this is on the iOS App Store and Google Play Store right now. So you can download it and check it out. It's pretty fun to play with. All right, so the second project I want to talk about today is a sea level rise viewer for American Samoa. So in the last talk, you heard about the Hawaii sea level rise viewer. And what we want to do is do something similar for American Samoa. And this is really important because American Samoa is one of, if not the most vulnerable Pacific Islands to sea level rise. And the reason for that is because it's not just a climate phenomenon that's affecting American Samoa, it's also subsidence. So the main island, Tutuila, is subsiding rapidly since an earthquake in 2009. And so most of the sea level rise projections that you see do not incorporate this properly. And what it does is it affects the timeline of impacts. The final answer in 2100 doesn't change all that much, but it changes the timeline. I'm going to show you that over the next few minutes here. So there's a couple of people working on this. My grad student, Carla Baizo, she's going to actually do the mapping and the wave modeling. We're working with Kelly Anderson Tagarino, a Sea Grant Extension agent in American Samoa. And she's connecting us to all the relevant people, government entities, community leaders, decision makers. And then we're going to work with PacIOOS to then take the Hawaii sea level rise viewer and port that onto a different site where we'll have information for American Samoa. Okay, so all right, so there's a lot on this slide. I probably don't have time to go through all of it, but the thing I want you to take away is to look at the bottom right. So the bottom right, the blue dots there, that's the GPS data from Tutuila. And so you can see how there's a very rapid sinking of Tutuila. And then layered on top of that is physics-based models of how that subsidence will evolve. There's some different colors there corresponding to different lithospheric viscosities, or like how syrupy the Earth's crust is. But the main takeaway is that there's a rapid subsidence in the near term, and then it kind of tapers off towards mid-century, right? So that affects the timeline. It affects the timeline of the impacts. So what we did was we took the interagency sea level rise scenarios that are existing, that people are trying to apply. We took out the vertical land motion or subsidence from those, and we replaced it with a physics-based modeled subsidence from this paper here, Han et al. 2019. So now we have realistic vertical land motion in there, and we can look at how these timelines evolve. And so that's what this table is trying to show here on the left. If you look down at 2100, so the first column is just taking the linear vertical land motion they use in the interagency report. The second one is using the physics-based modeled subsidence. The end result in 2100, that bottom row, was only a 14% difference. There's a 14% more with the model based. Not catastrophically different. You make plans based on that, you're probably okay. But in the near term, because of that rapid subsidence in the near term, you end up with almost 90% more sea level rise by 2040, and almost 70% more sea level rise by 2050 when you incorporate these realistic physics-based models of subsidence. This is really important to think about, not just the endpoint, and I think that's a key theme for anyone who's making decisions, not just the endpoint, but how you get there. And that's certainly something that I've been focused on in my work. Okay, so this example here on the right, that is actually the new sea level rise scenarios with those physics-based models incorporated for the subsidence. And so there's the observations there in green, and then the scenarios kind of branching out from there. So the final step here then is going to be to we've already started kind of mapping the extent of the impacts from sea level rise with the realistic subsidence, or more realistic subsidence. And then now the next step is then to work with PacIOOS and Melissa's team to get this information into a viewer. So that's where I'll stop, and thanks very much.
We have time for one quick question, if anybody has one. Sure, Ryan.
Great talk. This American Samoa sea level rise viewer, when do you think that's going to come online? And second part, do you have plans to expand this effort to other parts of the USAPI? Thanks.
Heather keeps asking me the same question. I need to talk to Melissa as well, I think. Probably, hopefully, by the end of this year, I'd hope that we'd have something fully operational and just ready to go and usable. There are no concrete plans to expand it elsewhere. I know that there are other tools out there working in different efforts, working in different areas. I think in terms of what we're doing, I think the real critical point is the resolution of the mapping, which is something that the people in American Samoa have expressed is not sufficient with some of the other tools available from NOAA, and also the realistic vertical land motion or subsidence. I think that's really, really crucial. Those are the two critical components that we're incorporating here, and whether or not those are both needed elsewhere, I don't know.
Thank you. Thank you so much for that great presentation. I hope you guys are, in the audience, taking away the importance of the partnerships into doing any of the sea level rise work that we're doing and the impacts to our region. Next, we have Dr. Curt Storlazzi. He is visiting us from Santa Cruz, California, where if you were in the last session, you learned about atmospheric river from Hawaii to Alaska. And as you may be aware, there's an atmospheric river from our region to California, just destroying, for lack of a better word, really the Santa Cruz coastline and other parts of California. So we'll keep that and keep Curt and his hometown in our minds. But I'll go back to introducing him. He is a senior research geologist with USGS Coastal and Marine Hazards and Resource Program. And he is focusing on how climate change and sea level rise will increase flooding hazards and reduce the resiliency of coral reef line coast and their associated communities in the Pacific. Thank you. Oops.
Well, I get to say not only aloha, but talofa and half a day. So today I'm going to talk about some work we've done being funded by the Pacific Islands Climate Adaptation Science Center and the USGS Coastal Marine Hazards Resources Program, work being done by USGS and UC Santa Cruz, trying to make consistent projections of coastal flooding due to both climate change and sea level rise to evaluate risk and to guide prioritization. I really appreciate the two previous presentations because this really kind of gets into the scale of the work we're doing now. With all future flood projections, we have the same issues as climate modeling. We need all of it. We need the global, we need the fine scale, but with all these, we trade scale for precision because we can only run computers so quick. So at the global scale, we kind of make these least common denominator methodologies. We model it, orders of kilometers. And there are really too many assumptions and too coarse results for place-based planning. On the other side, I'm showing the, the PacIOOS work that Terry showed earlier, super accurate. But the thing is to do it super accurately, we have to get at the scale that Phil was talking about, the scale of meters. And we just can't do that over massive geographies. And thus it's really difficult to kind of compare and contrast. And so the work we're doing right now is really at a fine enough scale to be accurate and thus used for planning, but over large enough spatial scales to allow for comparisons so that the different federal agencies can prioritize, because as with most federal agencies, we don't have enough money to solve all the problems right now. So we have to be able to do some prioritization. So how we're doing that is we're developing basically annual 20 and 100-year storm return coastal flooding projections at management scale resolution, so 10-meter scale. Like I said, Phil showed their work at a meter. Wish we could do it. We don't have enough computer processing to do that. And we do it for a number of sea level rise scenarios. I'm showing today the work my group's doing in the Hawaiian, Southern Mariana, and American Samoan Islands. Alaska, PI-CASC just funded this work for the North Slope of Alaska. I'm talking to my colleagues over in the Southeastern CASC to try to do this in Puerto Rico and the US Virgin Islands. And so these scenarios we developed in conjunction with federal, state, territorial, and local partners. And so you see that we don't have a specific, okay, in Hawaii, it's on Oahu, it's going to be 76 centimeters in 2100 based on the IPCAR3, because what happens is every couple of years that number changes. And so what we decided to do is just take some time slices and okay, we can adjust those, whether it's the new NCAA 5, the IPCAR6, but we're doing this consistently. We're doing this across the entire United States. And the return period storms, why we're doing those is because those are very general engineering considerations and also for insurance and investment purposes. So in terms of forcing, you saw a lot of work being done with the earlier, Tom was showing with the CMIP 5 scenarios. We've now taken the new CMIP 6. So these are the new fire scale models. These are actually now below a degree resolution. We can actually resolve cyclones, which is very important for waves and storm surges. We've taken 4 of those, and we've used those now to drive to compute future storm surges using the Deltaris's GTSM Global Time and Surge model. We have a reanalysis period from the era 5 for validation, then we run it forward with those CMIP 6 GCMs. We use future waves. We use NOAA's Wave Watch 3 model. Again, we have a PI-CASC phase that we use for validation. Then we run it forward with the global climate models. And so what we have now for the entire world is the first consistent model ensembles for both storm surges and waves. So we're not using this model to do, or this global climate model to do storm surges, a different one uses waves. Same models, same storm surges, same waves. It's actually the first in the world. These will be available soon for all of you to download and use yourselves. Then we dynamically downscale them, like Tara was showing you, using SWAN to basically kind of management scale, 200 meter resolution to driver coastal models. So in terms of the flood modeling, the top approach is what Tara and Phil showed you. When you have a small enough area, you can run a nice super high res 2D complete flood model. Of course, maybe a simulation may take you tens of hours, 100 hours. What we've taken is a new approach using the offshore, using a 1D models, them flowing into a 2D topographic model. And this runs on the order of an hour. And so we can do a lot larger areas, more simulations. We have a paper coming out soon showing that these basically match up very, very well at the scale of tens of meters. I always love to show flood Heather's house, and I guess it's Chip's houses and Phil's houses too, but here just shows some areas where we have spatially varying hydrodynamic roughness of those reefs because those really affect wave propagation. So you see the colors in pinks. And so then we shows a scenario. Heather, it looks like you guys are okay through 100 years with a meter sea level rise. So again, we're doing this for all these 3 storm scenarios, these 7 sea level rise scenarios. And we did this project was funded specifically to provide this information for the national parks and the fish and wildlife refuges. However, to do it, we had to do the entire islands because the way our model system was set up. And that's really nice because it's not just, oh, the rich folks in Waikiki get it, but it's, you know, the underrepresented Chamorro and Samoan and Hawaiian communities that usually don't get this. So we're actually providing some information that can help hopefully address some environmental justice issues. So along the 1,600 kilometers of coastline, the current risk for the 100-year storm are over 11,000 people, 13 critical facilities, 3,500 buildings, and $1.4 billion of infrastructure. That doesn't include DOD. And so there's 9 Indo-PACOM community facilities in there. So that number is probably a little higher than that. And the question is obviously, what's sea level rise going to add to those numbers? So again, thank you to my previous speakers that talked about the NOAA sea level rise viewer. So here's War in the Pacific's National Historic Park ASIN unit. This shows the amount of flooding with amount of inundation with a meter sea level rise. As in with most places, we have pretty high coastal dunes because we have energetic areas. There's not really much flooding except some water going up the stream. So here we show our 20-year storm with a 0 sea level rise. We start to flood part of the park with 25 centimeters, 50 and meter sea level rise. And so, okay, you know, we need something above and beyond just those NOAA sea level rise viewers. Same thing again, here's Kailea Pond, South Shore, well, south part of the saddle of Maui. So again, bathtub, okay, it just, you know, kind of comes up the face of the beach, but doesn't really get in there. Well, here's the 20-year storm now, increasing flood depths across the area. So great, the government makes a nice product. We drop it off, it goes into oblivion usually, but no. One of the things that we are required to do, and we do, is to work with our partners. And so what we're trying to do here is we have to provide deliverables. And the first is that to be able to provide these GIS map packages in a way that our partners can use that. And so what we've done is we've developed those interacting with Park Service, interacting with Fish and Wildlife, so that here is National Park Service incorporating our data layers in, they're matching up their assets, whether it's a monument, a toilet, a sign. So we've developed it with them so that they can use it. Then we also are going to make some pamphlets to help science communications to disseminate the products with them. That's one set of products. So over the past couple of years, our geospatial information group, led by Nate Wood, has developed this thing called HERA, the Hazard Exposure Reporting Analytics Decision Support System. And this decision support systems really helps communities understand how natural hazards could impact their land, people, infrastructure, and livelihoods by matching up USGS hazard data with data on buildings, infrastructure, and people. And that we're doing that with the US Census data and the US hazards data. And so here shows the HERA tool. In blue, you're seeing some flooding for the 100-year storm current sea level rise. What we then do is you can go into it and select, okay, let's look at how much critical infrastructure is in there. Or we can go in and look at how many people are in there. And you can look at, are those people under 16? Are they over 65? Are they minorities? What is your concern? And then there's different things on here. Overall statistics, we can compare in and amongst the different groups, and then you can export the data tables. So it really allows you, the user, to go in and address the questions you want to address. So it provides tools and data to help communities as they plan and prepare for natural hazards. So the other thing we've done is, thank you, been working with federal partners, basically FEMA and the Army Corps of Engineers for the past 2 years to keep sure the data is useful for their systems. And so what you see here is FEMA's FAST tool, or Flood Assessment Structure tool. You see the blues in there are some of our flood maps, the red are their assets. And so the goal of this is to be able to unlock federal funding like Bill and IRA, oh my gosh, the bipartisan infrastructure law, and I can't remember it, thank God, sorry. But those billions of dollars to keep sure that the federal agencies can suck our data into their systems to allow you to apply for it. So again, you see it in the systems, computing being calculated out, so seamless with them. So hopefully I've shown you, we're trying to provide some consistent, sound, cutting edge science to reduce risk, increase resilience, and better direct adaptation efforts. Thanks.
Thank you, Curt. One question. I know there's a lot of great information. You probably have a lot of questions.
Thanks. It was wonderful to hear incorporating the 100-year storm and storm surge into modeling and hazard adaptation. I was just curious, I might have been confused. I'm not a scientist, so I might have been confused with this, but are you folks incorporating with the 100-year storm sea level rise, just sea level rise, or are you incorporating climate change induced intensity and frequency of those storms and increased, say, precipitation and the impacts of increased precipitation meeting that sea level rise impacted storm surge?
Well, usually precipitation is not a factor here. We don't have big estuaries, so we're not taking into account precipitation, but we are taking, so sea level rise, so how much oceans rising, plus the storm surge on top of that, and then the waves on top of that to do the total water levels. And it is not, so it's not we're taking historical waves, we're taking future waves. So how climate's changing the directions of storms, changing wave heights, also how that's also changing storm surge patterns. So we're taking all that future information together.
So that they, when say we're dealing with hurricanes and whatnot, the 100-year storm cycle, right? A lot of the impacts we're seeing to our built environment are that combination of the Mauka or landward flooding meeting that storm surge and just, having nowhere to drain essentially for a while. So that's just curious, is precipitation with these storm events a factor in it at all, or are you aware of efforts being made to that?
We're not doing precipitation here. We're just doing coastal flooding, do that. So not joint coastal and pluvial and fluvial. So.
Thank you, Curt. And on to our last speaker of this session. And I did think if I did live near Chip or Phil that I would be safe, but I guess Curt will tell us in the future. But Dr. Fletcher, I'm sure you're all familiar with him. He is the interim dean of SOAS, the School of Ocean and Earth Science and Technology here at the University of Hawaii Manoa, and the director of the Climate Resilience Collaborative Research Team, where I did see some booklets over there, if you're interested in that. A professor and past chair of the Department of Earth Sciences and past chair of the Honolulu Climate Change Commission. His research focuses on assimilating global trends and decarbonization and climate projections, and looking at modeling and impacts of sea level rise in Hawaii. So please welcome Dr. Chip Fletcher.
Thanks, everybody. So I was asked to talk about a new research group that we have formed at SOAS, the Climate Resilience Collaborative, with money from the Office of Naval Research. We've just come out with our first annual report, and there are a few of them over there if you'd like to help yourselves. And then at the end of the talk, I'm going to refer to how some of the recent modeling products that you've been hearing about are being applied in policy development in Hawaii. The Climate Resilience Collaborative has a great online website. If you Google SOAS CRC, you can get there. There's a lot to explore. We have a number of partners. We are working with Tiffany Anderson, Doctors Tiffany Anderson and Haunani Kane in the UH Manoa Department of Earth Sciences, Wendy Maguro in the School of Architecture, McKenna Kaufman and her group in the Institute for Sustainability and Resilience, Doug Luther, who did the modeling that you heard about from Tara, is working with us. He's currently doing the same type of wave modeling for the South Shore of Oahu and getting prepared to go over on the windward side of this island. And we do want to expand it statewide over a few years. Phil Thompson, who you heard from, Nicholas Schneider and Anna Malai at the International Pacific Research Center, and the core team, which is the faded group behind us here. I'll be touching on the work that all of these groups are doing. Our goals are to produce research products in support of climate adaptation, and we're focused on sea level rise right now. We're hopeful that in a few years we might get more into storminess as well as heat. This is the first product out of Doug Luther's Wave Run-Up group. We are using digital elevation models that retain buildings. So all of the wave flooding that you've been seeing in the past few talks assume what's known as a bare earth digital elevation model, and then we put an air photo on top of it that makes it look like the buildings are part of the modeling, but they're actually not. Here we are actually retaining digital elevation buildings so that the wave flooding is forced to go around these buildings. This is flooding in Waikiki and Kaka'ako at 5 feet of sea level rise, which basically works out to end of the century under the intermediate high scenario that is available from the Interagency Task Force. Phil's group is working on installing tide gauges around the islands. We have 3 or 4 new tide gauges installed on Oahu to get a better understanding of how the water level variability around the islands works, and get a better understanding of extreme tides and the flooding related to them. We are using a shoreline change model produced by Dr. Sean Vatuzik. It's a 2-dimensional shoreline change model. The modeling for coastal erosion shoreline change that you are familiar with in the current PacIOOS viewer is 1-dimensional. Shoreline change in one location does not communicate in any way with the shoreline change a few tens of meters away. With 2 dimensions, we get a longshore transport as well as cross-shore transport. So we are going to be using this more advanced shoreline change modeling, plus we are using thousands of satellite images rather than just 4, 5, or 6 old air photographs. We're retaining the old air photographs, but we're adding now thousands of satellite images of the shoreline in order to better understand the historical nature of shoreline change, which constrains our future projections of shoreline change. And we are looking at the groundwater inundation problem. Dr. Shelley Habel with us has put in a couple of wells in Waikiki with funding through the City and County of Honolulu. We're going to be instrumenting storm drains. We're going to be looking at drainage failure, water level flooding in combination with rainfall as well as tidal flooding. So we're trying to get at the problem of compound flooding, which Ka'aina described nicely there in the back of the room a few minutes ago. High water levels, waves, and rain, these do happen. They are damaging. And the last one that, one of the ones you may remember was in December, about a year ago, with a Kona storm. The folks at the International Pacific Research Center are modeling heavy rainfalls, specifically from the question of marine heat waves. So we get these bodies of high sea surface temperature that settle in around the islands. How do these drive extreme rainfall events? They're also looking at atmospheric rivers and how they may be involved in local rainfall events. And then, as I just described, can we bring this all together to understand the problem of compound flooding? Very simply, when it rains at high tide, most of our urban area no longer has gravity drainage. And when you lose gravity drainage, you need to think about a whole new way to keep that area dry. It's not just going to be raising the land or raising the buildings. Perhaps we need to implement pumped drainage. So the PacIOOS viewer uses increments of sea level rise taken from assessment report number 5 back in 2013. We plan on producing a new viewer working with PacIOOS where the interagency task force intermediate scenario and intermediate high scenarios can be used to provide a chronology. These are available and modeled for every tide gauge in Hawaii, as well as all of these different hazards that I presented to you available as GIS layers, including the compound flooding. The folks with Wendy Maguro at the School of Architecture have been, they've actually now graduated 2 Doctor of Architecture students, and we have a few more that are working on the problem of what does Waikiki look like mid-century under roughly 1 foot of sea level rise, and at the end of the century under 3, 4, or 5 feet of sea level rise. What are the elements near the Alawai? What are the elements on the shoreline? What are some of the other locations? What are the elements in terms of design flood elevations, architecture, et cetera, that need to be considered? And we've held workshops with stakeholders getting their input as well. And McKenna and her group at ISR and the Department of Urban and Regional Planning are looking at issues related to shoreline retreat, identifying costs and trade-offs related to responding to sea level rise. What are the different strategies that might be considered? So we have, and PacIOOS with the Hawaii Sea Level Rise Viewer it's just blown everybody away about how this tool has been embraced, the use of research products to develop new policies. We have Kauai shoreline setback, which has been in place for many years, using historical shoreline change as a basis for determining the location of new construction and reconstruction of existing buildings. The new Kauai Constraint District looks at wave flooding and hydrostatic flooding or basic sea level rise flooding at mean high or high water, and identifies 1 or 2 feet of elevation above that floodwater surface for future construction. Maui has had a shoreline setback based on the rate of shoreline change that they were the first out of the gate in Hawaii in terms of developing a data-based setback. And they are currently working on a new setback that is in discussion right now in the community with the Planning Commission on Maui. Honolulu also has a proposed setback based on historical shoreline change. Again, an application of science-based information to determine where construction and retrofitting of existing buildings on the shoreline should be located with regard to safety to the problem of coastal erosion. This is bills 41 and 42, which are still in play at the City and County of Honolulu. The Honolulu Sea Level Rise or Honolulu Climate Change Commission has sea level rise guidance, which has gone through a recent update. Elevated rail through Kaka'ako has been redesigned. This was a few years ago based on the PacIOOS Hawaii sea level rise viewer, making sure that there was still sufficient clearance between a potentially 6-foot elevated roadbed and the lowest component of the elevated rail, making sure that the federal guidelines for truck traffic under there were still met. Also, they reorganized electrical components of their stations with regard to 6 feet of sea level rise. Hawaii now has as of June, the nation's first real estate disclosure law. If you are selling property in the 3.2 sea level rise exposure area, it must be disclosed to any potential buyers. And we have Act 17 passed a few years ago, the Environmental Policy Act, requiring that all environmental assessments and environmental impact statements must consider sea level rise. Bill 41 at the city and county is considering a rate-based setback 60 feet from the certified shoreline plus 70 times the annual rate of shoreline change, the annual rate of erosion. This is an example of what that looks like up in Laie. This line is available on the CRC website under resources. We have a layer on our map viewer where you can see where this line runs around the island of Oahu. How much time do I have left? That's 0. So I want to thank everybody. And maybe there's time for a question. Thank you.
Good timing. Yes, we have, we'll take one question for Dr. Fletcher. Any questions? Okay. Well, I'll just a little overwhelmed by our future. That concludes the speaker part of the Sea Level Rise Adaptation session. So please just give a round of applause to all the wonderful speakers and talks we just heard. Thank you.